Can we go back further? Well, yes, we can. It's harder to go back further with certainty. We're quite certain about the temperatures I'm showing you with these. These are hydrogen isotope graphs I've just showed you, based on the hydrogen isotope temperature data. But can we go back further? Well, we can. And we have other proxies for that. We have some of the same proxies we've been talking about, but we can look, for example, at oxygen isotope ratios in marine organism shells that are trapped in ocean sediments. Again, sediments form in layered structures, so we have a sense of what the time is that they were formed at. We can measure the oxygen ratios. That tells you something about climatic conditions at the times those shells were formed, which then sank to the bottom of the ocean and became part of the sedimentary, ultimately of the sedimentary layer or the sediment layer at the bottom of the ocean. So it's one example. Another thing we can do is look at fossils. You look at fossil leaves. Again, fossils occur in rocks. The rocks are layered. The layering is a rough indication of age. And so you can look at fossil leaves, and just the type of leaves you see tells you something about the climate. Was it tropical? Were these deciduous leaves? Was this a more temperate climate? And you can begin to learn something about climate from that. You can also learn something about the volume of ice. There are a number of indicators that give you the volume of the ice. You can tell whether sea level was high or low. And if sea level was low, that indicates that a lot of water was locked up in ice. And if a lot of water was locked up in ice, the climate was probably cool. So there are a number of indicators that take us substantially further back in time. They don't do so with the accuracy of the 150-year temperature record. They don't do so with the accuracy of those 1,000-year temperature reconstructions. They don't do so with the accuracy of the hydrogen isotope cores from Antarctica. But they do give us a rough overall picture of what the climate has looked like over the last, well, to be honest, the last 4 billion years, which is about the history of the Earth. The Earth was formed about 4.6 billion years ago. And I'm not going to describe the total history in all its gory detail. And again, the more recent times in that history we know better. But if you look at the history of the Earth's climate going far back, it's probably the case that the present day is relatively cool compared to the historical climate. By the way, that's somewhat of an interesting anomaly, because we know that the sun has actually been getting brighter over time. That's something that's worried climatologists, but they think they have it figured out. So the present is probably a little bit cooler, and the present has been experiencing this fairly rapid cyclic behavior in the climate associated with the ice ages and the warm interglacials occurring roughly every 100,000 years. And that's a fairly short time scale on the 4 billion year history of the planet Earth. So as you go back in time, into times tens to hundreds of millions of years ago, and here we're getting into the age of the dinosaurs, it was probably a lot warmer. How much warmer? I don't know. We can't really pin that down, but warmer. Significantly warmer. I mean, there's evidence of tropical-like fossil vegetation found in what at that time were continents that were in the Arctic, for example. So the Earth was considerably warmer at times in the past, at times 10 to hundreds of millions of years ago during the age of the dinosaurs. There was a time further back, probably somewhere between 200 million and a billion years ago maybe, when the Earth's temperature fluctuated quite a bit, but averaged maybe not terribly differently from what it is today. And that may extend back to several billion years, maybe 2 billion years or so, with considerable fluctuations. And then going way back into the early history of the planet, of course, we were formed in a very hot state, the heat due to the accretion of small bodies in the solar system that congealed together to make planet Earth and gave up their energy as heat when they collided together. So in the very early history of the planet, it was hot. At some point, it was too hot for life. But life formed probably well over 3 billion years ago and has been continuing ever since. So we have a climate record of a living planet that goes back billions of years. One of the most interesting things about that record, and something that's only recently come out, is there are probably situations, and they probably occurred somewhere between about 750 and maybe 580 million years ago, in which the entire planet froze solid. And we believe these times were associated with periods when continental drift had put most of the continents near the equator. The oceans froze completely solid. The continental interiors were completely dry. Dust blowing off the continents landed on the frozen ice and changed the amount of sunlight that was absorbed, and volcanic eruptions put gases into the atmosphere that, as I'll talk about in subsequent lectures, helped the planet warm, and eventually the Earth recovered from, in fact, probably very quickly, would recover from those states which are called snowball Earth. This is still somewhat controversial. Not all scientists believe they occurred, but there begins to be some pretty good evidence that Earth froze solid for several occasions. And if it freezes solid, you might worry, how will it ever melt again? Because ice reflects so much sunlight. How could it ever warm up? And the answer is there was dust involved and there were gases from volcanoes involved that let it warm up again. One of the interesting things about those snowball Earth phases is that we believe that they may have killed off a good fraction of the species that were living on the planet, but right after them, there were vast sort of explosions in the diversity of living things, including possibly the occurrence of land animals and the occurrence of complicated multicellular organisms. They may have some of their origin in these unusual climatic events called snowball Earth. So the climate has done interesting things going back in the past, and if we were to ask the question, is the Earth's climate, the question we started this lecture with, is the Earth's climate and particularly the change in climate we've seen in recent decades unusual? Yes, it's unusual in the context of the last 1,000 years. Is it unusual in the context of Earth's entire 3 or 4 billion year history? Absolutely not, at least if you talk about the magnitude of the change. It was a lot cooler than just the few degrees, the degree or so warming we've seen. It was cooler by 6 times that much during the most recent ice age. During the age of the dinosaurs, it was certainly warmer globally by a lot than it is now. So the Earth has certainly seen climate extremes, which are much more dramatic than the variation we've seen in the last decade. The more significant question is the variation in the last decade unusually rapid? Have there been very rapid oscillations of the entire global climate? And that is a question which needs to be answered. And that's a question that's a bit more subtle. We certainly know that as Earth came out of the most recent ice age 10,000 years ago or so, there were, at least in regions, parts of the northern hemisphere, for example, quite rapid excursions in temperature that occurred naturally. Did they occur globally? We're still not sure about that. So we don't know the answer to the question of whether the climate change of recent decades is unusually rapid, but it certainly is in the context of the millennium. And in the context of global temperature changes, it probably is unusually rapid. And as I'm going to show you in subsequent lectures, we understand the cause of the recent climate change. And that cause is things we're doing, and that's causing this very rapid climate change of recent decades.